today I'll present the paper to you written by Xu Feng, Kevin Schmidt, and John Spence on data collection strategies for time-resolved X-ray free electron laser diffraction and two-color methods, which was published earlier this year. And, oops, sorry. For some reason, I was in the GoToMeeting. To give you a brief outline of what I will be talking about during this presentation, I'll briefly give a short introduction into the methods part that will be indirectly used during or in this paper, and then I'll dive into the different paragraphs of the paper and ending up with conclusions. I won't elaborate too much on the crystallography methods because we already had quite a good presentation on that in the last journal club. So just as a very brief reminder, there are different types of crystallography. The goniometers based, oh, that's wrong, whatever. The goniometer based approach where you have one large crystal and in a loop, and then you take a rotation series of one single crystal. And opposed to that, you do have the SFX, the serial crystallography approach, where you have lots and lots of crystals into in a solution, and you use a nozzle or LCP or other injection systems to put them into the X-ray beam, and then every crystal is hit by an X-ray pulse once and destroyed by it, and the diffraction pattern is collected. Another important method in this paper is the so-called two-color FEL. And here, for a short introduction, I've chosen to base it on a paper also earlier this year published by Marinelli et al. And that's the current scheme used at LCLS, where they do not use annulators tuned for two different wavelengths with a single bunch, which was mainly done before. But here they do use two electron bunches that are accelerated to different energies. And then in a single, or in the whole annulator section, both of these bunches start to lace, and therefore you can have the full gain on both pulses, which gives you a lot more photons per pulse in the two-color scheme. And yeah, so with this technique you can get 150 femtosecond delays, and that's pretty awesome considering that you get the full power in the FEL. And so now this paper wants to do some cute things with all these different methods. And now the madness starts, as you can see. They start with a really basic introduction into diffraction, and I want to start there as well, where they say that the scattered intensity depends on several known factors like the initial or the incoming intensity, and well, you all know that stuff, right? And so if you want to sum up your signal, you can average over your whole ensemble of single shots. And to make that a bit more accessible, you do an approximation where you average over all the single things individually. So the average intensity of your average scattered intensity depends on the average intensity of a shot, your structure factor, the average shape transform in all directions, the polarization factor, and so on and so forth. And now you can group these things, or a few things together, because there are lots of parameters that depend on the crystal, like the shape transform or the polarization effect, and all that will be put together in this constant C. And then you can express your experimental structure factor by things that you can measure, or at least approximate in the case of C. So this is all known. Now the authors propose a new technique which uses the two-color scheme, where they want to use a first FEL pulse, which has its first initial intensity, sees some structure factor, and has crystal properties 1. And then after a short delay, which might or might not include a pump laser in between these two X-ray pulses, a second X-ray pulse comes in, and the same thing happens for the second X-ray pulse. And now the new thing here is that since the time between these two X-ray pulses is so short, one can assume that nothing on the crystal side has changed, so that one can say C1 and C2 are approximately equal. And then one can calculate the change in structure factor amplitude by taking the difference over the structure factor 1, which should all be known. And then a few conventions are made to make formulas a bit easier in the later parts, where the ratio of incoming intensities is called K12, and A denominates the scattered intensity fraction multiplied by K. And the pattern that results from such an experiment can be seen on the right-hand side, where you have blue and red Bragg peaks given by the diffraction of the two different wavelengths in the two different pulses. And if you choose your wavelength differential well enough, you can get a good separation on your two Bragg peaks. The third technique mentioned in the paper is based on a goniometer, where you have, like I said, a single crystal, and you take a rotation series of this crystal, and then the measured structure factor depends on your scattered intensity and the angle that you move between, your angle step. And since the step is independent of your single shot, you can take it out, so that essentially it is just the sum over the scattered intensities. And here they distinguish between two modes. One's below the Henderson limit, where you could take a whole rotation series, or when you're above the Henderson limit, where you have to make sure that you translate your crystal far enough, because you shoot a hole into your crystal with every single FEL shot. So now that we've understood the basics, we can get into the real juice of this paper, where they wanted to see whether one or the other technique has an advantage over the other based on error analysis. So how many patterns do you need to come to a conclusive result? And first they do the error metrics for the standard Monte Carlo approach, the standard SFX, where if you look again at the experimental structure factor, you have three quantities, and standard error propagation gives you the known formula dependent on the individual errors squared and then summed up and taking the square root of that. So that's all basic, I guess, undergrad physics. And then the authors did an approximation on these errors. Unfortunately, the order changed in from the second to the third line. So the 5.2 is the calculated error for catepsin B crystals that were used in recent experiments. And the intensity fluctuation at LCLS is expected to be around 10 to 15%. So the authors chose the worst limit, or the limit going towards the worst side, using 15%, so that they end up with an error number that, as expected, drops with increasing numbers of shots. And in order to be able to resolve a 1% change in structure factor, you need on the order of 80,000 patterns to drop this error down, so that you can actually extract about a 1% change in your time-resolved signal. So that's pretty bad, 80,000. But what happens if we go to the two-color approach, where, if we recall, the difference in the structure factor is pretty much square root of A minus 1. So the error is just proportional to square root of square root of A. And if you do the error propagation there, you end up with a rather nasty formula. But if you do the limit for large N, it boils down to a rather easy thing again, where it's inverse proportional to the intensity per shot, which is essentially the Poisson noise on your detector. So a strong hit is less prone to be falsified by Poisson noise, while a weak hit is more prone to do so. And the third summoned under the square root is essentially how stable is your K. So how stable is your intensity ratio between the two shots. And then the authors considered two different modes. One is the high flux mode, essentially what I've presented to you on the third slide, where you have full Sarsi pulses, two full Sarsi pulses, and you depend on the Sarsi effect twice. And since that is stochastic, K may vary a bit, or a lot. So, but since both pulses are rather strong, you can neglect the first two parts in the sum, because the intensity of your shots is supposed to be high. Then everything essentially boils down to the same thing as for the standard Monte Carlo approach, also with a similar prefactor. But in this case, we have the square root A times alpha factor. And in this case here, the alpha is the error of K over K, so the relative error for the intensity fluctuation. And if we want to resolve a 20% change in the structure factor, so square root A is 1.2, then we can tolerate up to 80% error on our intensity fluctuation, and we are still smaller on the error. And therefore, we can safely assume that we need less patterns for the two-color high flux experiments than we would need for a standard SFX experiment, where we hit every crystal only once. And then the second approach that one can do to do two-color or two-color-ish experiments is if you do split and delay, where you can really well characterize the energy difference or the intensity difference, because you take a fixed amount of your beam and put it on the delay path. That leads in a rock solid K, but the overall flux will be a lot lower because you have several mirrors to have the split and delay stage in there. So based on that, your error will be dominated by Poisson noise on the detector. And here, the prior knowledge that you get, since you probe your crystal twice, you already compensate for all the crystal effects, and therefore your prefactor is a lot lower compared to the 2.9 for the standard Monte Carlo approach. So here you already need a lot less patterns to get down to 1% error, which makes it possible to see 1% changes in structure. So here you need a lot less patterns. If you believe these numbers, then that would be around 100 patterns needed to get 1% in the structure factor. The last technique is the goniometer technique, where again with error propagation, you find out that if you're above the Henderson limit, then essentially you have the same thing as with all the high flux techniques so far. So whether it's the standard Monte Carlo approach or the high flux Twocolor, again, your error scales down with square root of n. But again, the prefactor is really, really low due to the fact that you probe the same crystal over and over, and therefore you already know the orientation and the crystal effects. And if you stay below the Henderson limit, then your error is pretty much independent of the amount of shots that you take, because it doesn't matter how far you rotate your crystal, you'll always have the same crystal again. Oh, well, that sounds wrong now, but it's you get what I want to say, I hope. So the paper presents 3 completely different techniques and dives into the math behind error metrics. Excuse me, that's my phone. I'll have to hang up briefly. Sorry for this disturbance. So let's compare these 3 techniques. As I've already said, the dose-limited goniometer approach is limited in its error and you can't gain anything by having more patterns. So that's why the blue line is horizontal, not changing with the number of patterns. Well, the other approaches do have this tendency, this 1 over square root of n, so that the error always drops with the more patterns you have. But the Twocolor approach has a huge head start on the error, so that you need a lot less patterns to get or to resolve a 1% change in structure factor. So that it would be beneficial to use this technique for time-resolved studies. So in principle, it all boils down to, if you do have prior knowledge about your crystal, in the Twocolor approach, it would be by probing the same crystal twice, or with a big crystal, probing the same crystal over and over again. That does help to reduce the number of patterns that are needed. And especially the Twocolor approach is really, really promising from what the authors found out. But there are also some drawbacks. If you recall, I said for the purpose of this paper, we assume that C1 and C2, the crystal factors, are the same. But they are energy dependent, so there are obvious limitations to this assumption, because in the two-color approach, we do need two different energies in order to resolve the two spots on the same detector. So therefore, this assumption hits its limits rather quick. But we'll see. This was all simulated stuff, but the experiment for that will happen in February. So I guess we're all really excited to find out whether it works like it's proposed in this paper or not. And now I think we should still have some time to discuss about that. Thank you.